All right. As people are streaming in right now, I think it might be a good idea to start, as we are now 10:01. And first of all, I would like to say welcome everybody who's joining us for this fantastic webinar on the final results and the case studies that we have achieved at the DECOAT project. We have a very interesting webinar for you in store today. I would like to first call attention to the fact that we have a very interesting program, of course. We will be joined in a couple of minutes by Guy Beule from the DECOAT project coordinator. He's from Centexbel, and he will be introducing the project to you, and then also introducing all of our speakers who will give you all of the details on the great work that we've done so far. This will also end in a question and answer session. So I would like to point out that if you have any questions, please use the chat to put them into the speakers, and then Guy will moderate the question and answer session at the end. So that being said, I think I would like to just say thank you everybody who has helped out in organizing this great webinar, and thank you all for showing up for it. And I would now like to introduce you to Mr. Guy Beule from Centexbel, who will introduce the project and tell you all about what our original intent was and who our next speakers will be. So, Guy, can I ask you to join us, please?
Thank you very much, and also all from my side. It's a pleasure to introduce to you our DECOAT project, because basically now we're at the end of the project. So we're convinced from our side that we can put together a nice program. And so what is DECOAT all about? Well, as the title says, we try to decode objects, and that you have to take quite literally, because we try to remove the coatings from objects. And there are couple of different ways to do that. One of the main goals was to see if we could develop coatings in which inherently we have a functionality built in that does not give a problem during the actual use of the coating, but that at the end of life allows to remove the coating from the substrate. And you see this here schematically represented. So it's let's say a small additive to the coating or an extra layer that can be triggered. And we will hear more about this and the other developments later on. But just to tell you that, yeah, this decoding aspect is the key thing, of course, of our project. Why would you like to do that? Well, if we look at, I would say in daily life, there are a lot of products that we use that have their functionality, that are, let's say, as comfortable, as practical as they are because of a coating. And that spans a wide range of different products. That can be about glass substrates or metal substrates. But what we looked in the project are objects made of plastics or made from textiles. And you see here some examples. So it can be like the cover of a mattress. That can be bags, backpacks, and so that are used for outdoor clothing, but also automotive parts or some like electronic switches or other small devices linked to electronics, to household goods, and so on. And so they have this coating that's nice from a practical viewpoint, but at end of life it poses a problem because the coating so far is typically a challenge, is a hindrance when you want to recycle the materials. Now, why do we need to recycle? I think that is quite clear. I think it's the last years a lot changed. And I think with our attitude to that, we're all in favor of circular material use. And one important driver for us also to start the project, since we're a European project, was of course the fact that from European side, there is a strong focus on more circular material use, be it in the plastic sector, be it in the textile sector. And for that, I just wanted to show here quickly the info on the EU strategy on plastics, basically to show that, yeah, now I think it's very much in focus, but we have to also realize that it is relatively recent. As you can see from the timeline here, the Commission adopted the EU plastic strategy only, or by now 5 years ago, in 2018. But in the end, that is not so long ago. If we look at the efforts toward textiles, it's even less long ago. And basically, the EU strategy for sustainable and circular textiles was published a bit more than a year ago. And why I want to mention this is that with DECOAT, we started the ideas of the project to work on the proposal to prepare this project around 2018. So just to put it in perspective, that we tried already from that time on to look a bit forward and see if we could find solutions to recycling coated materials. Now, if I say we, that's of course not only Centexpel, the organization from where I am, but we put together a whole consortium. And we do not have to go into detail, but I just wanted to highlight the different types of partners we have. So we first of all have the end users, so that are the companies who are producing nowadays coated products, coated parts, and who look for a solution so that their products can be recycled. And for the textile part, we have the VD, I think in Europe, a well-known producer of outdoor clothing. Then we also have Panasonic, so producer of electronics equipment. And then from automotive side, we have Mercedes-Benz, that is well known, and also a tier 1 provider, Meyer. And then to come to these solutions, we basically have 2 groups of further partners. That's on the one side, technology providers, so companies with innovative solutions that can help for this decoating, for the characterization of the coatings and so on. And then we also have the RTD, so standing for Research Technology Development Partners. So basically a couple of universities, one university and a couple of research centers, like Centexpel is one of those. And then a 4th group of partners that we have are partners doing the innovation support. That means help with exploitation of results, with the assessment from economic side, but especially also from ecological side, and then also partners who help with the dissemination. And I would like to mention explicitly ISWA, who was so kind to organize this webinar. So then a couple more just bookkeeping details, I would say, about the project. Just to give you an idea about the size, we received just below 6 million euro funding from Europe to do this project. We were funded within Horizon 2020, and we started beginning of 2019, and now we're at the end of the project. And I want to stress again, this start in view of the current focus on sustainability, on circularity. When we started the project, that was definitely not so much the case yet. And one thing I also wanted to mention is, we as Centexpel are coordinator. Why do we try to do that? Well, in general, we already have for several years a strong focus on sustainability in Centexpel. That means like resource efficiency, but that also involves things like recycling. And this just as one slide with that respect. So DECOAT is a European project that we coordinate, but we try to do that also for different product types or for different materials. Like we have one project focused on the recycling of PVC. We have a project focused on floor covering in general, also one dealing with textile and clothing. And I would say the important aspect for today is that in these other 4 projects mentioned here, that also deal more or with a stronger focus or a smaller focus on circularity, we're always also confronted with how to recycle coated objects. So in that sense, I think DECOAT is really a very nice one and a very necessary element of going to circular material use. That was it as a bit of background. Now, if we go back to today, then you can see here the agenda. So we will cover different aspects that were developed within the DECOAT project. First of all, there will be an intro from the side of my colleague Ine, with more deep going view on the project. And then we will have some specific elements highlighted. That is about the solvent-based recycling, the mechanical recycling, also the assessment of the environmental impact, the eco-design potential, and then a part also on the exploitation. So looking at innovative business models. And with this overview, I would like to end, but not without acknowledging the support that we got from the EC for doing this project. So we're really thankful for that. And also from the side of our project officer, I think he's a very flexible and pragmatic. So I don't know, thanks a lot for guiding us through the whole project lifetime. And with that, I would like to end my part and give the word to Ine for a deeper look at DECOAT.
So thanks a lot, Guy, for the introduction. So as mentioned, I also work at Centexbel, so I'm a colleague of Guy. And I would like to give you some more insights on the DECOAT project, so diving a little bit more into the project itself. So as already mentioned by Guy, we are focusing on coated and painted items. So why do we put these coatings and paints on the bulk material in the first place? Actually, we have a threefold reason. It can enhance the performance. For example, it can protect the underlying bulk material from UV. It can give additional functionalities. For example, it can waterproof a bike bag, and it can simply improve the aesthetics. But on the other hand, these coatings and paints, they hamper the recycling process at end of life, meaning that these items are nowadays either being incinerated or landfilled. So what do we want to do? We want to actually recycle the bulk material, so we need to remove these coatings or paints from it. And it's actually the missing puzzle piece to go for a fully circular approach. So actually here you see an overview of the full concept that we want to achieve. So it goes from several products at end of life that we want to recycle, but it's really important to see here that we're really aiming at the fully closed loop. So we want to have end of life materials, do the reprocessing, and make again the same materials from them. But I will dive more into the separate parts during the presentation. So within the project, we worked on 4 demonstrator cases. So on one textile use case, it's a bike bag from Vaudet. And then from the plastic use cases, we have the sockets from Panasonic. We have a dashboard part from Mercedes-Benz Turk. And we have an interior automotive part from Meyer. So if we take a look at the recycling loop, actually the core of DECOAT is actually that we want to introduce an additional step in this recycling process. And this is a step where we do the debonding of the coating from the bulk material. It can be done in several ways, which I will highlight now. So we have 2 strategies for the coating removal. Either we can debond it via triggerable coating, but for this, we really need design for recycling, as we need to implement an additional layer or triggers during the design phase of the product. The second strategy is the solvent-based recycling, and this can actually be done on conventional products. But design for recycling can aid also in this case. For example, if you are choosing to put a more easily dissolvable coating on top of the bulk material. So first we will take a look at the triggerable coating strategy. So then we need this part of the recycling loop. So you have already seen this before. So as he's explained, between the substrate and the top coat, we put in specially designed triggers. During the use phase, they are inactive, but at end of life, we can trigger these. This can be done thermally or via microwave. And at this point, at the triggering point, we enable the separation of the top coat and the substrate. Within DECOAT, we really focus on the recycling of the substrate. The top coat for now is still waste, but maybe other projects can also assist here to do something useful also with the top coat later on. If you look at the type of triggers that have been developed in the project, we have several types. We have core shell materials which need heat upon triggering. We have superabsorbing polymers who need moist to be triggered. We have magnetic particles and carbon nanotube-based particles who will need a microwave to be triggered. And then we have the Indar Inside technology from Rescol, based on blowing agents who needs also heat to be triggered. If we take a little bit more, some insights on the materials. So these core shell materials and superabsorbing materials, they are actually added in the conventional primer layers or base layers. We just add them to the formulation. But what did we see is actually that not all particles lead to a successful debonding. If we take the core shell materials, then actually we didn't see any debonding at all. So these were not effective. We had the superabsorbing polymers, which induced a very local debonding. As you can see also from this plastic part, we can remove the coating upon point of impact of the steam gun, but it's so local that it's really not industrially viable. So we discarded those two routes in the project. A third one are the microwave susceptors. So we checked quite some different types of additives and we could really identify which were most responsive. And we can see actually very rapid heating. But unfortunately, we didn't see a really nice coating debonding. In some cases, you can even melt or burn the substrate material, which is of course not the intention. But they do have a very rapid heating. So we built a microwave pilot line also based on the rotating drum, where we can actually also do debonding of the plastics and textiles. And then we are looking at combining this microwave susceptors with the Indar technology, which needs heat upon triggering. And in that way, we are looking if we can have a more energy efficient debonding process, that we can use microwave instead of a conventional oven. If you go more into detail on this Indar technology, so this is for the moment a solvent-borne primer, which is based on blowing agents. So between the substrate, either the plastics or the textiles, you apply this primer layer and then you put the conventional coatings or paints on top. In case of plastics, we do the triggering at 150 degrees Celsius. For the textiles, we need slightly higher temperatures, 180, because a textile, the standard, for example, a polyethylene coating is actually cured at 150 during the production. So we need to be at least 30 degrees above the production temperatures. So we do the triggering at 180. And we can actually see that the coating can be removed quite nicely. With infrared analysis, we didn't see any residues left. And also in case of the textile, it can be very nice if we can have a washable primer layer, and also we can tune the formulation to have a more wash resistant version. But what did we see is that the performance was actually dependent on the substrate and the top layer thickness, especially in case of textiles. There we saw the more smooth the surface was, the better we could debond the coating. And also the top layer thickness plays a role. If you have a thicker coating, it's more easily to debond it than you have a very thin one. Here you have some examples of the use cases. The first one is a polyurethane foam with a PVC foil laminated on top, and then we have the Indar primer in between. And with triggering upon heat, maybe not that visible on this picture, but you can see that the PVC foil actually really delaminates from the PU foam and can be removed. Second one is the automotive part. Here you can see that the paint can be nicely removed. Same from the sockets. And the last one is the textile sample. Here we have a polyester substrate with a polyurethane coating on top, and you see upon triggering it that spontaneously delaminates the coating, so which is also a nice result. Then we have a second strategy, which is based on solvents. It uses the equipment of the Creasol from Fraunhofer IVV, but I will not go into detail on this part as Johannes will present that very nicely in the presentation after me. Then we have, of course, a first step, which is the sorting, which also needs to be taken into account. So there we use a fluorescent dye as a marker, and by using this fluorescent dye we can do an identification of a sample and also redirect the waste to the corresponding debonding device. For example, if a certain additive, it might need heat to be debonded, or it might need, for example, to go to the creosote process. So that's why we chose two fluorescent dyes, the coumarine, which is when we add that means that this sample will need to go to the solvent-based debonding. If it's rhodamine B, it needs to go to the heat triggering. And we simply mix this fluorescent dyes in the formulation, and then when you do the identification, you can assess if the sample will need to go to process A, for example, solvent-based, or process B, the heat triggering. So then we did optical monitoring. There we used the Polo LED technology from Fraunhofer IVV or hyperspectral cameras from the partner Iris. And at Iris, a pilot line was also built in the project where you can actually do the separation of the different types of fluorescent dyes and so on. So here you can see that it works as a conveyor belt system, and then you do the separation dependent on the type of fluorescent dyes present. Then the next step in the loop, after the triggering, you still have the debonded coating and the bulk material still together. So we still need to separate those, but there we rely on conventional techniques which are already in place in the recycling industry. It can be, for example, density separation, but also we are using air zigzag separation and so on. And after we can separate substrate and coating, then the coating is going back into the recycling process via extruder. And we have again the secondary raw materials, which again can be used to make the starting products. Just have an overview of one of these plastics use cases. So here you see the input. It's painted plastic parts using the Indar primer. After optical sorting, we do the activation step, we grind it, we do the separation step, compounding upcycling, and then the output are these pellets, which can be used again to make novel fascias. More details will be given by Vicent in also the coming presentations. Of course, we did quite some material studies in the project, especially partner CTEC did a lot of those. So we checked the aging of the samples because we needed to know if the coating was still functional after aging, if we can still debond it. So that was one thing we looked at. We looked at the coating performance. If you put an additional primer layer in between, we still need to make sure that we achieve all the functional requirements. So like the coating adhesion and so on. We also looked at the influence of the debonding process. For example, when you bring the material into contact with solvents, we need to make sure that the solvent didn't affect the material too much. We checked at the simple recycling. For example, how many recycling loops can we do? What is the effect on the material properties? Do we need to blend it with virgin materials? I have here, for example, one example. So it's the remaining coating residue and then the impact strength. So if you have the impact strength, you see when no coating remains, you have a very high impact strength. But on the other hand, if you have the full coating remaining, you can see a quite severe drop of the impact strength for the ABS material. So then you can see, for example, if you have around 40% coating remaining, that it's still feasible to have quite sufficient material properties. And then, of course, we do quite some recycling loops. So we have up to 5 loops for certain parts where we always do the painting or coating. We do the debonding, we do the reprocessing, we have like the pellets. And again, we go for the starting point and we do 5 loops of these. And then we blend it also with virgin material. Of course, very important also are the supporting actions. So we did a life cycle costing study because we are actually adding an additional step to the recycling process. We need to make sure that it doesn't affect the economic viability of the process. So we need to know the effect of the cost of the whole system. So this was being assessed. We did a life cycle analysis because we needed to know the environmental footprints of the recycling steps we are added to the process. And we did a risk assessment. For example, if you're adding carbon nanotubes-based materials to a coating, we needed to make sure that it didn't pose any risk to human health. So this was also thoroughly examined. So this is a bit in a nutshell the project, and I also would like to finish off by saying in nature nothing is created and nothing is destroyed, but everything is transformed. And that's actually also what we are doing in DECOAT. We are transforming the waste into novel materials. So this was a bit in short from my side.
Thank you very much, Ine. You gave a very nice overview of the various elements that we cover within DECOAT. We'd also like to mention that please, if you have questions, put them in the chat. As indicated in the beginning, we will deal with that at the end of all the presentations, but please don't wait till then to post questions if you have already now about this presentation or in general. And then we will move on to the next presentation, and that will be given by Johannes, who will present us the CreaSolve technology and how it was used in DECOAT. So Johannes, feel free.
Yes, thanks, Guy, for the announcement. So hello, everybody. I would like to start with a short introduction of myself. My name is Johannes Schneider, and I'm working for the Fraunhofer Institute for Process Engineering and Packaging, or short IVV. I'm working here since for 2 years now in the polymer recycling, and our focus is here on the solvent-based recycling, mainly on packaging, but in the course of the DECOAT project, also on coated plastics from, for example, the automotive, the construction, or from textile waste. And
Johannes,
so today,
sorry for interrupting. Yeah, sorry for
yes,
interrupting, but we still see the last slide from the presentation from Ine. I don't know if you
really,
already tried
okay.
to move it.
Do you see it now?
From my side, not.
Ah,
Because
sorry.
normally if you do the take control, and then there should be the arrows to move it just below the slide on top.
Yes, yes, I know. In the test it worked. Hmm.
Yes, now it's there.
Now it's there. Okay,
No,
perfect.
I'm sorry to interrupt. I just took control.
Okay.
Johannes, why don't you just tell me when you want to move it, and I will move
Yeah,
it
okay,
forward.
perfect. Thanks, Jose. Then we'll do it like that. So today I will speak about the solvent-based recycling of coated plastics and textiles. As we move to the next slide. Can I? Yeah. So the Fraunhofer Gesellschaft is, I will start with an introduction about what Fraunhofer means. So Fraunhofer, the Fraunhofer Gesellschaft is Europe's leading research society for applied research, and the Fraunhofer IVV is only one of 76 institutes all over Germany that are conducting research in practically all application relevant fields of technology. Just some examples are microelectronics, material science, life science, and of course, how we can deal with the huge plastic waste problem that we are currently facing all over the world. And our budget is composed of 30% base funding from Germany's state government and the federal governments. And the rest, 70%, is generated by public and industrial research projects. The next slide. You can see that in Germany we have a wide range of non-academic research organizations, which Fraunhofer is one of. But there are also other organizations like the Helmholtz-Gemeinschaft, the Leibniz-Gemeinschaft, or the Max Planck-Gesellschaft. And these organizations are having different research focuses. So some of them, for example, the Max Planck Gesellschaft is more conducting basic research, and if you want to say, Fraunhofer is at the other extreme of the research focus that you can have. So we are conducting applied research, meaning that we are aiming at bringing the developed technologies at our institutes into industrial application as fast as possible, often together with industry partners. And on the next slide, you see that, as I initially said, that contract research is a mainstay of our activities. So this is, as you can see here, equally distributed into publicly funded research, so funded by national governments, or in the example DECOAT from the EU, and 50% is also bilateral research contracts with industry partners. So this is equally distributed here. The next slide, we are coming to the Fraunhofer IVV as the institute that I am working for. And this is located in 2 cities in Germany. The larger part is located in Freising, which is close to the Munich airport, so very close to Munich, where our central is located. And a smaller part is located in Dresden, which is in eastern Germany. And in total, at the Fraunhofer IVV, in both locations together, 300 employees are working, and most of them are working as scientists, as you can see. At the next slide, we see our different business fields that we are working on. So coming from an origin as an institute for food research, our research started in the 1940s in the business field food. And we are still conducting research in that topic, for example, on plant-based substitutes for meat or dairy products. And then coming from this food research, also other research topics were derived. For example, safe and with increasing importance, recyclable packaging for example, food products, then processing machinery for this packaging, and also product performance in terms of sensory perception of food and also the packaging materials. And with the upcoming problems caused by the packaging waste and the increasing amounts of petrol-based polymers, our business field, recycling and environment, was generated, which is conducting research, for example, on recycling technologies. This leads us to the recycling. It's at the next slide. In general, there are 3 different types of technical solutions for plastics recycling. The first one, it's sometimes referred to as energetic recycling, but basically it's just incineration. So the plastic waste is burned. Typical combustion gases like carbon dioxide or nitrogen oxides are produced, and the energy can be used. Of course, the energy of the combustion process. The second solution for recycling is a chemical recycling, like, for example, the sulfolysis or the pyrolysis. And during chemical recycling, the polymers are decomposed either into their monomeric units that then can be polymerized to a new polymer, or into basic chemicals, feedstock chemicals that can be reused in all kinds of different chemical processes. And the third solution for recycling is the material recycling, where, in contrast to the chemical recycling, the polymer chains remain intact. So one option for that is the mechanical recycling, where the polymers are, easy said, just remelted and brought into a new shape. Of course, it's more complicated than that, but simplified, it's just a remelting process. And then there is the solvent-based recycling, where the target polymer is selectively dissolved and then separated from the undissolved rest and then dried. And one example for that is the Creasolve process, which is displayed here. This was developed at the Fraunhofer IVV. And on the top of the slide, you can see the principle of the project. This process enables the targeted recovery of pure polymers from mixed waste streams or, for example, composites. So a mixed waste stream enters the process as the input material, and then in a first step, the target polymer, and only the target polymer, is dissolved using specific and safe solvents that are specific for this process. Then the dissolved polymer is cleaned, and impurities or contaminants can be removed in that step. For example, this can be brominated flame retardants or plasticizers in the polymers like phthalates. And after this cleaning process, the polymer is dried. So the solvent can be recovered and after a treatment be reused in the process. And after drying, we get a product with a very high purity, which is free of all the foreign polymers that were in the input waste and free of impurities and harmful substances like flame retardants or plasticizers. And which has a quality comparative to virgin material. Coming to the DECOAT project on the next slide. Thanks. Our goal is to use this process, this Creasolve process, in an adapted form to enable a material recycling of coated polymers. Here the principle is not to remove the coating, is to remove the coating from the substrate and thus enable a recycling of the substrate material without a loss of quality. So the coating is removed and we can then mechanically recycle the substrate material. In the case of the Creasolve process, this primer that is displayed here in our DECOAT picture is not needed. So the top coat can be applied directly onto the substrate. So we can work with products from state-of-the-art production and coating processes. And our goal is that after showing the technical feasibility at laboratory scale, we want to upscale this process to a 10 kilogram per batch pilot plant. On the next slide, you see the principle. So in contrast to the Creasolve process, here the target polymer, so the substrate material, a textile or a plastic substrate, is not dissolved, but the solvent and the processing conditions are chosen that the coating debonds from the substrate. And at our laboratory, this happens after this, the principle that you can see here. So the samples are put into a beaker together with the solvent. The temperature needed for the debonding process can be applied by a heating plate, and friction is brought into the process with a stirrer. And at laboratory scale, we observed 3 different debonding mechanisms that I will explain later a little more detailed, but they can either dissolve or delaminate due to the solvent treatment. And thus the processing conditions had to be adapted for each substrate or coating material and combination thereof, depending on their specific debonding behavior, and of course the residence times and temperatures needed to achieve this debonding. If we go to the next slide, we see the first debonding behavior. So in the cases where we had coatings which are not or not so heavily cross-linked, the coating could be dissolved with our solvent used. So in that case, the input, of course, had to be grinded in the first step to feed it into our process. Then during the solvent treatment, as you can see in the picture below, after some time, the coating is more and more dissolved from the substrate. This was a polyamide textile with a PU coating. And then with an easy filtration step, the textile can be separated from the solvent with the coating, and then be dried in a first in a drying oven and then in a degassing extruder, and we regain a pure textile material. In this case, it would be a PA as a granulate that then can be reused in any reprocessing process. The solvent, as you can see, is recovered from precipitating and drying the coating, and of course also from drying the textile material, and then the solvent can be reused in the process. On the next slide, we see the second case. Here, when we are facing more heavily cross-linked coatings, we do not achieve a dissolving anymore of the coating because the cross-linkings are too heavy. But then it often was possible to delaminate the coating as a whole from our substrate material. This means in terms of processing that an extra separation step is required to separate the coating from the textile material, which are both swimming into the solvent. So this could be via density separation or other separation steps that would then have to be included in an industrial process. But the rest of the process would be the same. The third debonding behavior that we observed was that the coating delaminated as a fine, it looks like a powder that goes into the solution. So it's removed from our substrate, but it's not totally dissolved. It's still there in our solution, but it's like a fine powder. So it can be filtrated more easily with a coarse filtration step. And then we need a second filtration to get the fine powder from our solvent in the solvent recovery, but we can recover our substrate material with a single coarse filtration step. And then, of course, drying is like in the other two use cases or in the debonding cases. Coming to the next slide, we see, of course, we performed analysis of our products, and this was performed with FTIR measurements. And easily said, this measurement method can be used to identify materials because every type of material, every polymer, every material gives an individual infrared wavelength dependent pattern for reflection pattern. And in our case, we use this technology to distinguish between the substrate and coating material. And so here we see a result where it was possible to remove the coating. So we see that the typical pattern of the substrate material, and in green, the typical pattern of the coating material. And after a solvent treatment, on both sides of the sample, there's only the pattern of the of the substrate material left, so no residues of the coating are found at our sample anymore after our solvent treatment. On the next slide, you see that in the course of our project, we performed lots of tests with all different kinds of textile and plastic substrate materials. So we used polyester and PA textiles. We used different substrate materials, PU, ABS, PC-ABS from automotive or electronic applications, and all different kind of coatings, polyurethane, PVC coatings, acrylic, silicone coatings, and different kind of lacquers. So a huge variety of different materials and material combinations that were tested at laboratory scale. And on the next slide, we see that for most of the combinations tested, we could successfully debond the coating from the substrate material without any residues, which was confirmed by FTIR measurements. But of course, we also had some challenges. For example, when the coating and the substrate material had a similar dissolution behavior. So both materials tended to dissolve under the same processing combinations. And in that case, either the coating only swelled, but it was not completely removed, or the substrate material swelled and or dissolved partly together with the coating. So no strict separation of both material was possible in that case. Or other coatings just did not debond due to our solvent treatment. And here it was, for example, one silicone coating that we tested on a polyester textile. But as I said, for most of the combinations, it was successful. And then in the next step that you can see on the next slide, we upscaled that process to a small technical scale, to our small technical plant, after finding suitable processing conditions for the samples in our projects. And of course, depending on the process adaptations that we needed for the respective material combination. And here we used a small small technical plant, which is still, of course, a small technical scale, but it showed a first upscalability of the developed process in our DECOAT project. So here we used a grinding mill to cut the material. Then we used different dissolving tanks and drying tanks to perform the solvent treatment and drying of the material. And in the last step, our degassing extruder to get rid of the last bit of remaining solvent and produce a granulate that then can be easily processed into any application for the material. On the next slide, we see that for upscaling, we selected then 2 demonstrators for the solvent-based recycling process. Our first demonstrator were PC-ABS sockets coated with a DECOAT from Panasonic. And the second demonstrator was a polyester textile coated with a slightly cross-linked PU coating that at laboratory scale showed a dissolvability. So we processed both of these materials at the pilot line that I've shown and successfully received PC-ABS and a PET recyclate with, as you can see, very good properties. So with GPC measurements to determine the molecular weight, we measured that only a slight decrease in molecular weight over the recycling process was happening. So for the PC-ABS, it was like 6% decrease in molecular weight, and for the polyester, it was only below 1% of molecular weight loss over the whole recycling process from input material to the final granulate. And And then these recyclates that we produced were then sent to our project partners to perform mechanical testing and perform the reprocessing into their initial application to show the circularity of our developed solution. These tests are still ongoing in the final month of our project, but we already have quite good results. For example, a filament of the PET textile of our PET recyclate could be produced by melt spinning at Sandexbell. To give you a short outlook on the last slide with topic, we have seen very nice results. So the dissolution, the elimination of the coating works for different kinds, for most of the coating substrate combinations that we had in our project. But currently we only showed the applicability on very pure waste streams. So if we are facing different kinds of substrate materials or different kinds of coatings in one waste stream, this could lead to problems caused by these foreign materials that might not be removed by this kind of process. And yeah, according to the state of the art, there are currently no pure sorting fractions for coated plastics, from example, from construction waste. So yeah, we would have to have a fraction where we get the waste that we want to recycle. So the important step is that a collection and sorting system is established, and then we have a process that is ready to recycle these waste materials. But yeah, as I said, currently there are no such sorting fractions. But if they are there, and they are often very heterogeneous, then the Creasolve process could also be a suitable option, where not only the coating is removed, but only the one target polymer that we want to extract from this waste stream is dissolved. The rest is removed via, simply said, filtration, and our target polymer is dried in the end and recovered. So this will finish my presentation. Of course, we want to acknowledge the European Union for funding our project, and I would like to thank for your attention and give back to Guy.
Thank you very much, Johannes. I think it showed very nice how powerful Creasolve and solvent-based recycling can be, and also how versatile to deal with different materials. And judging also from the questions, I think there's a lot. So I think there's a clear interest in the technology. And also thank you, Jose, for guiding us through the slides. So now we can move on to Vicent, who will present on mechanical recycling. I don't know, maybe we do a trial, Vicent. If you could move the slides yourself, I think that will be the easiest. It works. You're just still unmuted, and then we can start. Vicent, you're still unmuted.
You're mute.
Yeah, okay, sorry, my excuses. I was muted,
Okay.
but actually I'm in control of the presentation. For some reason, the first slide is missing. I will introduce myself. This is Vicent Martinez, senior researcher in AIMPLAS. Very quickly, our organization, AIMPLAS, we are a technology center with more than 30 years experience in the plastic industry, providing solutions to companies throughout the value chain, from raw material manufacturers to plastic processors and end users. Our main activities include the management of research, development, and innovation projects Also, we cover technological services, including laboratory analysis, testing, and prototyping. And also, we are very active providing training and organizing technical events related to the plastic industry. So my topic in this seminar is the mechanical recycling of plastics coated parts using the bonding methods featured in the DECOAT project. So as a quick outline in my presentation, I will start highlighting the role of plastic materials in the circular economy, main benefits and also disadvantages of coated plastic parts, the approach of the DECOAT project in the mechanical recycling of these plastic coated parts, and also I will share with the audience some results from the mechanical recycling for two case studies, the automotive coated components and also some decorative electric parts. So let's start highlighting the benefits of plastics that comprise a wide range of synthesized materials that offer good mechanical strength, low weight, good barrier properties and wearabilities when exposed to the outer environments, good thermal sellability and welder capabilities, and AC processing and design flexibility by several techniques. The overall plastic convenient properties allow to increase its use in several applications, substituting conventional materials such as metal, glass, or ceramics. Plastics durability, ubiquity, and adoption in large volumes for some applications implies also a responsible management of the waste generated in order to avoid environmental impacts, promoting a transition from the linear to a circular economy in which we keep resources in use for as long as possible with almost zero waste generation. Circular Plastics Alliance is an initiative within the European Strategy for Plastics in the Circular Economy that is aimed to the reuse of total 10 million tons of plastic recyclage in the manufacture of new products by year 2025. This is quite an ambitious objective, considering that, according to Plastics Europe, the total European plastic converters demand is approximately 60 million tons. The main sectors in the plastic materials demand include the packaging industry, also the building and construction sector, automotive components, other parts in the electrical and electronic industry, and other minor sectors. Currently, plastic recyclage poses some limitations for upscaling. First of all, there is a need for sourcing large volumes of plastic waste for proper collection and recovery. Typically, the post-consumer mixed plastic waste streams require sorting and cleaning pre-treatments. And for some plastic waste products, they feature complex structures in multilayered laminates, fiber-reinforced parts, or assembled products that can be contaminated, mixed with other materials, or also there is a risk of contamination with substances of concern due to the presence of remaining additives, halogenated elements, or even heavy metals. So that the importance to adopt harmonized standards in order to assure homogeneous recyclage with quality similar to the virgin plastic grades, and also the need to implement regulations or certification protocols that assure traceability on plastic recycling content. So within this scenario, as my colleague highlighted in the first presentation, the DECOAT project is aimed to develop methods to separate the coatings from the bulk material, ending up with easy to recycle parts, and contributed in this way to a more feasible circular economy. So now let's focus on plastic coated parts. Plastic substrates can be coated with paints, varnishes, and lacquers to enhance surface properties and aesthetic appeal, allowing scratch resistance, better weatherability and UV resistance, providing smooth surfaces with a special finishing effect, such as metallizing, pearl, or other iridescent finishings, allowing customized coated plastic products that can be tailored to the needs and decided of individual customers in small batches. The typical applications for plastic coated parts are in the automotive and transport sectors, in components such as bumpers, inserts, coverings that are coated in different range of colors, and also in the electric and electronic sector. Some decorative parts or components include coated plastics, as the main polymer types are typically the styrenics, such as ABS, SAN, PS, and also other technical polymers, such as polypropylene or even polycarbonate. The main coating techniques, especially at industrial level, include coating by means of spray guns, roll coating, screen coating, or also, for some process, curtain or deep coating. But also there are some disadvantages related to the plastic coated parts. We have to bear in mind that the plastics materials show inert and low energy surfaces that require high energy treatments in order to increase, to enhance wettabilities. That means, in most cases, the application of primers or adhesion promoters in order to assure a good adhesion or bonding of the coating layers. Also, these coatings are based on solvent-based paints and varnishes that attack and etch the plastic substrate and might cause swelling, softening, or even dissolution of the polymer substrate. The coating techniques in the final stage implies the drying and curing at high temperatures that could lead to head deflection and dimensional changes in the finished plastic parts. Also, other important issues are relating to the recycling of these coated parts at their end life, because these coating layers are strongly adhered on the plastic substrates and are difficult to remove after curing due to the thermoset nature of these coating layers. Some typical methods that have been proposed in order to remove the coating layers include chemical methods, such as soaking in alkalis or salt solutions. On the other hand, physical methods by means of eroding the coating, these coated layers, using high pressure water jets, solid mixed with solid glass particles in order to blast, to erode the outer surface of these coated parts. But these methods, generally speaking, have shown low effectiveness, especially when implemented at industrial levels, and also consider that if some coating impurities remain after these erosion methods, they can affect the mechanical performance of the plastic recyclates, especially reducing the impact strength. So that in this framework, the DECOAT project approach for the bonding on demand feature the incorporation of triggerable additives in the primer layer applied onto the plastic surface. These activation methods rely on the heating or also microwave activation for the coating, the bonding, and Emma's colleague also shown in the first presentation. And in our case, we also cover the mechanical recycling of these coated plastic parts after the sorting and the activation stage. So now let me share with you 2 case studies that we have developed within the development of the DECOAT project. First case study comprises the mechanical recycling of automotive component, specifically an interior dashboard panel that was manufactured by means of injection molding by partner Mayer, and afterwards the coating by means of gun spraying techniques. The first step was the application of the Rescol partner that developed a debondable primer that can be activated by means of heating thermal activation by means of heating in a oven cabinet, reaching temperatures up to 150, 160 degrees for 5 minutes. So after this thermal activation, the coating layers can be removed, actually peels off the plastic substrate. So at the end, the whole plastic part can be is free of these paint coating layers. So that in the second stage, we proceed with the reading of this whole plastic part in order to reduce to particle size in between 8 to 10 millimeters, and also performing a zigzag electron separation with airflow in order to remove the small particles and also the tiny coating layers that could remain in the material, in the stream after the reading process. At the end, these ABS plastic granulates are the input material for the compounding stage, in which we blend the recyclate with ABS virgin grade, and also we add specialty additives. In our case, we incorporate impact modifier in order to upcycling the quality of these ABS recyclate pellets that were reused in the manufacture of new panels. During the development of the DECOAT project, we managed to perform up to 3 recycling loops in which we mechanically recycled, obtained the ABS recyclate pellets for 3 different loops, so that at the end we were able to compare the performance of these ABS recyclate materials after each loop. So as a main outcomes for this case study, we were able to assess that the activation and separation of remaining impurities are in the limit below 4%. Also, although I would not provide too much details, during the compounding and upcycling process, we were able to introduce an innovative supercritical CO2 stripping technology that allows us to remove the total volatile organic compounds in the ABS recyclates to a limit below 50 micrograms carbon per gram of sample, so that the new molded parts after each manufacturing process show a smooth surface with no irregularities and good optical and aesthetics after each coating process. According to the results from our colleagues in the CETAC laboratories, they obtain different test specimens in order to compare the mechanical performance. And as you can see in this in this graphic, although there is a decrease in the impact strength after each loop for the blends, the recyclates incorporating up to 30% of recyclate ABS, we are very confident that the reduction in the impact strength is in a range in between 10–15%. So this is a very positive outcome in the sense that the recyclates after each recycling loop contributes to maintain the good mechanical performance of these ABS recyclates, and so that the incorporation in new ABS panels components for the automotive sector can strengthen the sustainability of these materials when adopting these the bonding strategies as we develop in the DECOAT project. And for the other case study that comprise these decorative electric frames that were manufactured by partner Panasonic, also incorporating as a primer layer the Resco debondable primer. So that we proceed in a similar way, so that after activation in the heating cabinet, the coating layers can be removed, can be actually peel off from the plastic substrate, and after performing the shredding and separation stages, eventually we are also able to obtain these ABS plastic granulates as an input material for the next compounding stage, in which we also blend these plastic recycled granulates with the virgin ABS grade, and also adding the impact additive modifier in order to eventually obtain these recycled ABS pellets that were also used in the manufacture of new frames for the same application. This reuse is still ongoing, and we are confident that the performance of these ABS recyclates will allow the manufacture of new plastic ABS frames in the same application. So this is okay. This is the end of my presentation.
Thank you very much, Vicent, for the clear overview of the different tests done on the mechanical recycling and the nice results. I think now we can move on from the more pure technical work to some of the what we call in the project supporting activities. And that is first of all about the eco-design aspect, and therefore we will go to Natalia, who will tell us about the potential of eco-design for debonding, for decoating.
Hi, good morning, everyone. We'll try to navigate the slides. My name is Natalia. I'm a senior sustainability consultant in EcoMatters, and as Guy introduced, we are performing the support activities for the DECOAT project. And in particular, we were involved in the life cycle assessment of the case studies and in development of the eco-design tool. EcoMatters is a sustainability consultancy focused on the life cycle thinking. And we're situated in the Netherlands, working with a wide range of industries. Thank you very much to my colleagues who already explained in great details the solutions that were in consideration. But basically, to put it in a very, very simple words, what is happening is that while coating of the parts of plastics, enhances the performance and helps to achieve the quality and functionality that the parts needed, they hamper recycling processes and the end of life. That is why in the end of life, as it happens now, the coated plastics goes to incineration and landfilling, and decoating solution help to debond or detach the coating from the parts and free the substrates for recycling. So in simple words, we add some processes to achieve gaining the substrate for recycling. The question is whether it's worth it, right? So whether there, what are the benefits of these processes? What are the drawbacks? Does the impacts of the added processes outweigh the benefits that the providing the secondary material brings? It is all very good questions, and the answer is always depends. So it depends on the industry, depends on the circumstances, depends on the part, depends on a lot of different things. So to help industries to navigate through the application of the DECOAT solutions, we came up with an idea of developing an eco-design tool. So the idea is to help industrial partners and predominantly manufacturers to identify the eco-design strategies that they can apply in their products based on the DECOAT solution. So answer whether the DECOAT solutions are applicable for their products, and if yes, then what are the benefits, what are the challenges, and so on and so on. So the main objective was to develop a simple communication tool that would help indicating and outline the strategies that the industries could then take further into the development together with the particular solution developers. Sounds great, but it is not as simple. What we have faced is the eco-design paradox challenge. Basically, that says that, yes, it is the easiest point of the product development and technology development to indicate hotspots and to fix the hotspots in the early stages of development. However, this is also the stages that are the most challenging as for the certainty of information and due to the fact that we don't know the scales of the production, we don't know which particular sometimes materials are used even. So to address this challenge, we deserted to the sustainability assessment levels concept that basically juxtapose or matches the technology readiness level with the sustainability assessment levels that are possible to apply and reasonable to apply in each of the stages of the development. So for the early stages, the TRL 2, 3, 4, 5, it is possible to do some simple checklists, hotspotting, screening studies, and for the further development, we can already get more upscale data, high certainty data, and introduce some quantification into the assessment. So the same framework we try to apply also in the process of the eco-design tool development. And at the first stage, we come up with the alpha version, a qualitative tool that was distributed internally within the project, and we focused really on hotspotting of the different solutions. And then followed up when we reached already a suitable pilot scale or upscale data, we were able to introduce more higher certainty and quantitative assessment and develop the final version of the tool. The second challenge that we faced in the eco-design tool development is the development dilemma, which everyone faces in all of their work, I think, is that it is not possible to do high quality work with the cheap investments, small investments, and a very short time spent. And that's the same in design tool development, but also in design, in eco-design use application. So the high quality results you want, the more time and cost you have to spend to collecting the data. And in the research process, not always justifiable. So we, in the project meeting with all the partners, we came up with a trade-off between the specificity and user-friendliness of the tool. And based on that, also came up with the conceptual structure of the tool that would emphasize this trade-off and focus first and foremost on the user-friendliness of the tool. So the main structure is as follows. The industry or the user inputs very simple set of the input data, so about the industry that it belongs to, what is the substrate material, what is the coating, what are the performance parameters that are necessary to meet. Then the core of the system matches this input with the most suitable solution developed within the DECOAT project. And here we were talking only about the two solutions that were presented by Johannes and Vicent. It's solvent-based recycling process and the interprimer, the triggerable primer. Yeah, and then the tool would communicate that to the user that this is the solution that we think is the most suitable for you, and then provide some additional information about the environmental performance, the economic performance, circularity, safety, and so on. Consequently, we also split the tool into two parts. First is a very easily accessible, low effort tool that focuses on compatibility, and this is an online tool available for everyone, that's possible to just put in the data and get the most compatible solution. And then the second part is the spreadsheet that provides or that requires more input data, more quantitative data, like, for example, the amount of substrate, the amount of coating, the surface of coating, but also provides a way more detailed advice and the assessment. So practically, that's the concept. How we went to the population of the advice is we went back to our industrial partners and to our technical partners and developed in a questionnaire and a series of workshops the main points that are the points of interest for the industries. Why we using eco-design tool, how we using it, what are the main points that we need to consider in the information that we're providing. As a result, well, I will present you some screenshots of the tools themselves, but you can also go online and check them out. The first is the online tool. This is the landing page that gives the short introduction to the tool. Here are the very simple inputs of the information that we ask from the industrial, from the user, from the position, hopefully, of industrial partner. So it's industry, the substrates, the coating, and yeah, the additional performance indicators. And it provides you the advice on the output one of the two. So it would be this on the left, the solvent-based recycling process, on the right, the inter. So it's two different output results. So it does not advise two at the same time. And of course, the context of the technology developers. And as the follow-up, you can also download an Excel tool that would give you a bit more advice. And when looking at the tool, the inputs are very similar, but as I said, they have more granularity and more quantitative data. So, for example, it's asking the amount of the weight of the part when it's coated and when it's not coated, and yeah, and it's this asks very similar but more detailed questions about the coating as an area of coating, and more specification about the end of life and waste scenarios. So, for example, if it's you plan it to recover post-consumer, post-industrial. As a result, there is a summary that brings you to the same result of a recommended solution, but with more information taken into account. And you also have a possibility to check the alternative solution to that. And as the second part, the summaries also providing a score in performance in 5 core categories: is compatibility, environmental performance, circularity, business economics, and safety, and provides an aggregated score. And this aggregated score is also developed based on the multi-criteria decision making and the expert survey that we conducted with the partners of the project. We can also check how the performance changes if we use renewable energy, renewable electricity in production, if we use renewable energy in debonding processes, and if we start considering downcycling instead of recycling. To go quickly through the additional advice, so each of the 5 core categories have its own page if a user wants to know more about this. So first is the compatibility. It would provide you the information about what is the level of the testing or expectations that is applied to this combination of substrate and coating. And also what to keep in mind regarding the use of the part. So in contact with water or high temperature or solvents, or if it's applicable with multi-layer coating solutions. Then the second one core is the environmental performance. And here we take in life cycle analysis perspective on environmental performance, and we base our assessment on the high level screening life cycle assessment. Based on very limited information that is provided within the tool. So please keep in mind that it's very indicative. And it's based on average European production processes and average European electricity mixes or renewable energy mix was taken, for example, Swiss renewable electricity mix. In the circularity and material use, we're using the UN recommended metrics for circularity, and we measure the share of the product that can be recovered and brought to the secondary material market and adjust this coefficient on the quality degradation if and when it's happening. And we also can estimate how much waste generation is avoided due to the DECOAT solutions. As for the business and economics, it gives the score based on the assessment, high-level assessment of the operational costs connected with the added processes, juxtaposed to the or like compared to the revenues that can be generated from either selling secondary material or cost savings from avoiding waste treatment that otherwise would have happened. Also, based on the life cycle costing, would indicate the hotspots in the costs structure and provide some information on what else good to know regarding, for example, capital goods or upscaling. Regarding safety, and that's the last category, we provide also 2 assessments based on the 2 factors: is occupational health and safety for the processes added due to the debonding solutions introduction, and the chemical safety of the solution itself introduced to the production. To summarize, so we have now a publicly available tool available for all interested parties. it is intended to be a starting point for the users to show the relevant solutions of the DECOAT project for their situation, and provide some baseline information on the 5 main indicators, main categories of the performance. Yeah, and we hope that this will help the industries to have a high early stage hotspotting and applicability of the DECOAT solution and introduction of these solutions into their own systems to improve the performance of their products. For more information, you can find anything on the DECOAT official website or on some parts on our website of ECO Matters, and of course to reach out to me via email. I think that's it from my side.
Thank you very much for sharing some of the insights, I would say, and the challenges for eco-design, and then of course especially for presenting the tool. I do hope people are triggered to take a look at their website. It's definitely a nice tool to best to play around with. So thank you very much. And then we will go on with the last presentation of today, and that will be given by Manos, and he will talk about something a little bit different, but about the innovative business models that can be used for also forwarding this type of developments.
Good morning from me also. Okay, let me go to my slide. Yes. Just a quick introduction on me. I'm also a materials engineer, and my postgraduate studies are on coatings and alloys. But recently, I mean by the last 10-15 years, I've been working on mainly on exploiting and supporting companies in exploiting their research results and supporting them in doing their business plans, exploitation plans, marketing plans, feasibility studies. So I was more involved in exploiting results from research projects. Now, briefly, the context of this presentation is an overview of the recycling industry, business modeling. What is business modeling? What are traditional business models? What do we mean by innovative business models? And some examples of the textiles and clothing sector on innovative business models. Now, the market size measured by revenue of the recycling facilities industry is 9.4 billion in 2022, and the growth rate of the recycling facilities industry is expected to increase to be 4.6%, which is quite impressive. On the other hand, what is more impressive is the global waste recycling services market, which was valued at $55.1 billion in 2020, and is estimated at $57 billion in 2021, and expected to grow considerably in the coming years as consumer awareness about the environmental impact of waste increases. It's expected by 2028, the forecast of the global waste recycling services market will have reached a value of almost $90 billion, registering a compound annual growth rate of 4.8% during the forecast period from 2021 to 2030. So this is a growing important market. Now, recycling and waste management is not so easy, and there are mainly concerns from industry. Company owners and shareholders think that it provides costs. It's another ring of the chain, bringing more complexity, again, more costs. It lowers efficiency of the production, and the final products have less quality than when using virgin materials. And these are the problems that we need to address by appropriate business models. The definition of business models is the plan to escape competition with the market by Investopedia, is the plan implemented by a company to generate revenue and make a profit from growth. And in simple terms, it describes the logic of how an organization creates, delivers, and captures value. It composes of 9 building blocks, mainly targeted to the customer. Who is the customer, the final buyer? How do you approach him? With which channels, and what are the relations to your customers? What's your value proposition? what are the key activities in order to reach the customer, what are the key resources you require, who are the key partners, at the end point, which are your revenue streams and how much would it cost for you to provide to your customer. These are the building blocks of a business model. Business model, the basic model is to earn something, to earn by making profit, selling a product or a service by more than it costs for you to produce it or to provide the service. But many successful businesses don't directly sell anything. They act as middlemen or brokers for other service providers. We will see examples of that later. They earn money by saving the customer's money, or they stay in business while putting the welfare of people and the planet ahead of the profit motive. So these are other types of thinking, of logic behind business models. Game changers in generation, for example, Wikipedia is the biggest, not employer, I would say, engager of people globally, right? There are 63 million people working systematically for Wikipedia, updating, upgrading it, enhancing it, right? While Wikipedia has only 300 permanent paid employees, I would say. Right? So this is their business model, use volunteers. Another type of business model is a benefit corporation. For example, Patagonia, Ben & Jerry, Etsy, Cabot. They give equal weight to social, environmental, and financial impact of their activities. They just don't make products and sell. What they sell is environmental impact or social impact. Power purchase agreements, long-term relationships, they actually reduce the building owners on the local energy grid. That's another type of thinking, another type of business modeling. And of course, a sharing economy, peer economy like Uber, Divi, and Skillshare, where you share, it's like an exchange of goods. You earn in Uber, for example, you earn extra income by using your own car. On Skillshare connects people who want to learn a new skill. And the game changers in the generation is Internet of Things, robotics, cloud, artificial intelligence. So any type of innovative, let's say, business model that we consider must or should incorporate one or all of these game changers. Very briefly, 9 disruptive, innovative business models. We'll share the presentation, so if you click on each of them, you can get in more detail. Some of them we already quickly describe, like the freemium, you get something for free, and then you want to upgrade, but then you have to pay for it. Subscription model, very popular, as we'll see the case studies later. Free offerings in the beginning in order to attract customers. The marketplace model, you create your own environment for different types of products. Sharing economy, premium experience like Apple, pyramid model, which as you go in more premium products, you have to pay more. Create your own ecosystem, and the on-demand model. The ones that are found that are more applicable in the textile and clothing industry, in circular economy, is coordinating circular value chains through data, circular product design, use, reuse, share, and repair, collection and reverse logistics, and sorting and pre-processing. That will be explained in the case studies with, let's say, with the examples. Quickly, some examples from existing companies. Globechain is a B2B marketplace. It's actually a platform that collects and reprocesses products like furniture, equipment, office supplies, and it makes revenues by charging membership fees. Similar as the building as a material bank, again, is a platform for exchanging and selling goods, mainly from buildings, from restructuring, refurbishments. In our case, Adidas, right, the Spring/Summer 21 release Futurecraft Loop model. There was the first running shoe that's made to be remade, right? It was designed in such a way so that when you manufacture and recycle, it can be returned to Adidas, broken down, and be reused to create new performance running shoes. Circos, another very interesting model, is for baby clothing. because babies grow very quickly. So they return the clothes, and with a monthly fee, customers have access to high quality clothing from different types of brands and delivered also to their door. They deliver to their own house. The clothes is interesting because they also clean, redistribute, and this way they eliminate waste and capitalize on clothing value while creating also providing also convenience for customers by delivering on their door. Other examples, it's H&M partnered with ICO to collect 29,000 tons of textile for use and recycling. And in return, it gives vouchers to customers for purchase other H&M clothes. Mr. Green Africa, a plastics recycling startup, they buy collected user consumer plastics and industrial waste as feedstock and sell recycled plastic of different colors and qualities. Two main, let's say, trends is the collaborative consumption platforms. These are online platforms that are emerging where individuals can sell, buy, or exchange second-hand clothing items. They facilitate peer-to-peer transactions and contribute to extend the lifestyle of textiles. Some even offer value-added services like they repair, alter, and they encourage users to repair and use clothing instead of discarding it. Another trend is traceability and transparency. With growing consumer demand for sustainable and ethically produced goods, companies are leveraging technology to provide transparency in the textile process, incorporating blockchain or other traceability systems to track and verify the origins of materials, ensuring responsible recycling practices and building trust with customers. As the need for sustainability and circularity increases, the industry is likely to witness further advancements in creative approaches to reduce textile waste and promote a more sustainable future. As Dame Ellen MacArthur said, circular economy waste is not an option. Products are designed and optimized for a cycle of disassembly and reuse powered by renewable energy sources. Thank you.
Thank you very much, Manos, for presenting these models and making think about how economy works, I would say. Now, thank you all for staying, first of all, with all the presentations. And as mentioned in the beginning, we can now deal with some of the questions. I don't know if you will be able to cover them all, but maybe the first thing we will try to do is to do a quick round over the speakers, because I think there are a couple of questions basically to avoid some misunderstandings and so. And then we can see afterwards how much time there is for some of the more deep going questions. I trust also that we will follow up on these questions, if not now, and then maybe or later on through mail or so. So first of all, I think Ine, when you presented, there was a question, and I think it's also very relevant in general, because you mentioned about thin or thick coatings. What exactly is thin? What is thick? What kind of coatings do we look at in the project?
Yes, it depends a little bit on the type of substrate you are looking at. If we look for the textile parts, we have been working with, for example, for the sockets, you have a coating about 10 microns, and then more for the automotive part is around 40 microns in total. So we see it's easier, for example, to debond the 40 microns than compared to the 10 microns, but it's still feasible to remove the 10 micron coating layer. We don't know what the lower limit is. 10 micron was the smallest amount we applied for the plastics. But the plastic is more easily to debond because it's a very smooth surface. A textile is a little bit more complicated. Like, for example, the one I showed, which was delaminating spontaneously. There we applied 2 layers of 100 micron wet, meaning that in total dry, that will be around 100 micron probably. So this one, then you have a 100 can nicely be removed. If, for example, you would apply a 10 micron layer on a textile, I think it will be very difficult because it's combined with the roughness of the textile, and it will rather break than you can peel off in one nice layer. So it depends a little bit, and it needs to be checked what this combination of substrate, material, and so on.
Thank you. Then maybe one other that I think is also relevant for quite some of the developments we do is there was a question about, of course, it's nice, let's say, to put a kind of trigger in a coating, but at end of life, how can a recycler know, yeah, this coating can be triggered?
Yeah. So in the DECOAT projects, we chose to use the fluorescent markers for this. Of course, you have to be aware that DECOAT is a low TRL project. So it's really more demonstrating the feasibility of the technologies. For example, the sorting with the fluorescent dyes. If you would implement it really in a value chain, then I think you need to agreement among all the players in the value chain, from the people who produce it up to the recyclers, and then you will need to have a consensus of which type of fluorescent dye you will use for which trigger. But this is something that will need to be agreed upon within the sector. And I think maybe also later on, if we know, for example, like the digital product passports are also upcoming. This was not really in the DECOAT project, but I also think there you will be able to retrieve quite some information on how you can recycle certain objects. So I think also from that viewpoint, there might be information be available that will give some input on the which type of triggers and the corresponding debonding device that you can use.
Very much. We go through the presentations then. Johannes, I think there was also a question, first of all, to very well understand the technology. It was if Creasolve is used for dealing with the coating after debonding. So I guess that was not fully clear. Maybe you can tell how exactly we can separate and dissolve.
Yes. We have to differentiate here between the Creasolve process and the solvent-based debonding process that we have used here in the DECOAT project mainly. So the solvent-based debonding means that we use our solvents that are coming from the Creasolve process, but we use the solvents to dissolve or to delaminate the coating from our target polymer. And the Creasolve process is using the solvents to dissolve the target polymer. So in case of a coated plastic where we are not able to remove the coating with the solvents, then the Creasolve process would be an alternative option with the target to dissolve the polymer that we want to recycle and leave the coating as an undissolved residue. So in our project, this is an alternative to the solvent-based debonding mechanism.
Thank you. And then I think some questions that show the interest. It was about how far is the technology developed? What is the TRL level? Is it possible? When will it become available? Are there some pilots, some demos?
Yes, I read a couple of questions in that direction. So at our research institute in Freising, we have a plant which is even larger than the plant that we used in DECOAT. This plant is currently built up or being finalized, and this has a TRL of 5 to 6. Sorry, I need to check that. Of 5 to 6, then there are industrial demonstration plans on TRL 6 to 7. There is an industrial demonstration plant in Indonesia dealing with polyethylene at TRL 7, and there are plans, one in Germany it's an industrial demonstration plant at TRL 7. At TRL 6, and there is one for polystyrene. I read that in the chat as well. Some already wrote it, which is from PS Loop. So dealing with polystyrene in Terneuzen in the Netherlands. So it is currently being being used on industrial scale. There are plans being built up from industry partners from us. but there is no company who is running the process and where you could send your waste to and they are recycling it. So it always needs, for example, a recycler who is working together with a plant manufacturer who who set up such a recycling plant to recycle the waste of the recycler. So there's no industrial company that is just using the Creasoft where you can send the material to it. It always needs to license our process and build up a plant.
Thank you. We'll also ask Vicent. I think there, when looking at the questions, there was one thing about the impact modifier, just to be sure. I think there was some doubts. Do we need to use it? When do we need to use it?
Well, it also depends on the final requirements foreseen for the product. I mean, in our case, especially in the automotive sector, there are quite stringent requirements. So according to the final properties decided for this product, you need to incorporate specialty additives. In our case, we tested in a preliminary trials that impact strength was a main requirement, so that in the upcycling stage, we include formulation of the recyclate, the incorporation of this impact modifier in different percentage from 1.5 up to 3 or 6% in some cases. But yes, according to the final requirements and specifications, it is advisable to incorporate specialty additives in the recyclate formulation.
Thank you. And then there was also a question if it would be possible to deal with acrylate coatings.
Well, in the scope of the DECOAT project, we focus on the, let's say, most typical thermoplastic resins, including styrene, ABS mainly. Also, we perform some trials with some parts made of polycarbonate ABS. So also it depends on the needs of the manufacturers. In our case, we cover products and plastic prototypes manufactured by injection molding, which are also suitable for covering all these mechanical recycling stages that are implemented at a large scale. So as long as you can source coated plastic parts as a waste stream based on these thermoplastic materials, I see more benefits using let's say these more commoditized thermoplastic materials.
Thank you, clear. Then if we move on, maybe also about the tool that was designed. And I think it showed very nice some of the aspects, some of the results and so that it can bring. But I guess eco-design is quite, as we saw, also complex and quite large thing. So when people use this tool, what they should be aware of are the limitations, what, let's say, can be expected, what not.
Hi. Yes. Yeah, I think that the main limitation is that it is an indicative tool, right? So it is a good tool to look at the main listing of benefits, possible advantages, but it cannot be used as a life cycle assessment tool or circularity assessment tool for your particular part, right? So it's if you have a part in mind, or your particular product in mind, then it would not be suitable to use this tool just to calculate your carbon footprint, right? Or to calculate your circularity index, because it is a high-level indication and it does not substitute the analysis for a particular product, I would say.
Thank you. And then with respect to the business models, I don't know if there was anything specific, but maybe just also to have there's something in what struck the mind is that we all know that, let's say, these solutions are better for environment if we can recycle, if we can have circular use, Manos. But nevertheless, it seems to get the things out there that we might need these new innovative business models, that it's so difficult to get people convinced, even if there's an extra cost to use these. I don't know if you can say some words about how business model can help there.
Yes, let me go to my slide, the one referring to the companies, because this is the main point, that to convince companies, because the demand exists from customers. Customers are getting more and more aware of sustainability and of environmental issues, right? United Nations Sustainable Development Goals agenda is promoting it globally. So the demand is there. So we have to convince companies, and the way is that if they can see that that circular economy and waste management is not a burden and not an extra cost, but it can provide, actually could save money, or if it's an extra cost, it could also bring more revenues, more income, that this will cover the costs. And this can be done by business models, innovative business models, like I say, using more volunteers, or the platforms exchanging materials, clothes or textiles. Or the baby model was very, I like this very much, that where they return the baby clothes, which are not damaged, and then they are refurbished and sold back. So this type of innovative business models, which some of them does not cost at all. It's very simple to set up a platform. I think all countries now globally set up platforms for exchanging used clothes. So some of them are cheap, easy to be done. It just need decisions from stakeholders.
Okay.
Okay. Yeah.
Thank you for clarifying. And then I see there are a couple more questions also popping up. Maybe one thing we could immediately pick onto, because I think it's very relevant, is about the Rescol debonding primer and what the TRL is there. I see the question is mentioned to Vicent. I don't know if you want to answer, or Ine from, I don't know who of you wants to answer about the TRL of the Rescol debonding primer.
Well, to my knowledge, the development of the Rescol debonding primer is at a very mature state. I mean, have managed to assess the convenience of this Rescol debondable primer on these mainly ABS plastic substrates, and the performance by means of thermal activation has been successful. So also other issues can be related to the specific applications and the compatibility of this primer with other specific coatings. But during the development of the project, the assessment of the performance of the Rescol debonding primer has been successful.
Yeah, thank you. I think I would also say it's indeed a primer in principle is a commercial product, so it can be used. I guess it always comes with a package on how to best use it, how to develop the specific application for it. And I think that also covers the question that there was about, is the DECOAT technology open to all? It is not that we develop, let's say, open IP. Huh? If you look at the solvent-based recycling or the mechanical recycling or the primer, but the goal is, of course, that these elements can be taken further and can be used by companies, or for further development can be used. But of course, then, it's an agreement with the partner. It is not that it's just, let's say, if you would think in software terms, that it's open source. It has been developed, but the goal is to take it further. For example, like mentioned in the question about the licensing. I see just also one practical appearing, Natalia. I don't know if you also see it, but it's about the eco design tool. And about
Yeah,
apparently still
noted.
some-
We will try to fix it. Yeah.
Yeah.
Yeah, we'll check what's going on. Thank you for noticing.
Yeah. And then maybe I know we're 1 minute before time, but maybe one last question, because there were quite some also related to the solvent-based recycling. I know, Johannes, there was also about, can you deal like more with the thermoset material, like from polyurethane or polyurethane coatings in general on textiles? If you can maybe as a final question, comment on that also.
Yes, so we have dealt with PU coatings. Some of them have successfully been removed in the process. If they are heavily cross-linked, then a delamination is more is usually the way to go, or the way the material behaves. But yeah, I read PU hot melts, for example. This was not in our scope in the DECOAT project yet, so we don't have experience with this, so much experience with this kind of material. This would have to be tested, but if it comes out that the coating is not debondable with our solvents, then still the Creasolve process could be an option, as I said, just to dissolve the target polymer and leave back the PU, for example, a hot melt. And for hot melts in packaging for PU adhesives, hot melts, we have some good experience for the Creasolve process, so we can get rid of these in our process.
Maybe I can also comment if we, for example, have a polycarbonate polyurethane, then the coating is rather delaminated. If we have polyether polyurethane, then, for example, the coating is rather dissolved. So it depends a little bit on the type of chemistry. And for the textile use cases, we added up to, for example, 2% of cross-linker and did not really impact the behavior. So that's also a little bit more in detail.
Yeah, thank you. Addition. Then I would say thank you all speakers for the presentation, for answering the questions. As mentioned, we would really do our best. I guess we have the contact details to cover still uncovered questions later on. And I would also say, feel in general, if you would like to know something more about the project, feel free to contact us. I would also, before finalizing, really want to thank all the partners in the project, because here you have, let's say, some of them that could present, not all, but you can see here on the slide, as also mentioned in the beginning, we are more, and the results shown today were only possible because of the collaboration with all. So I would also really like to thank all the partners, and once more for the EC funding that we received. So with that, we've come, sorry for the slight delay, to the end of the webinar. If you would still want some info, please feel free to visit us on the website, the LinkedIn page, or directly contacting us. So, and thank you very much for attending, and wishing you still a nice day. Bye.
Thank you. Bye.
Thank you. Bye bye.